Hello, students. This is Professor Ron. What I want to do today, since we didn't have our lecture due to the impending hurricane, hopefully we won't sustain so much damage and we'll get through this okay. I wanted to go ahead and complete section 5.8 on the integrals that we worked with. That is, we use the inverse trigonometric function calculus to generate some very useful integral formulas. So I want you to be able to see some examples of that so that you can complete your homework and then also complete your quiz. So let me go ahead and share my screen. I've acquired a new document cam that I got from actually from Japan. It worked out pretty well that they were able to deliver it fairly quickly, which is kind of amazing, but I'm not arguing. Now, what I want to do first is to remind you of the actual formulas that we derived. Remember, when we compute or derive a derivative formula, we naturally get a formula for integrals. And so what we found is that we have these three Pythagorean integrals. That is the integral of du divided by the square root of a squared minus u squared is the inverse sine of u over a plus an arbitrary constant, where we have the restriction u over a less than 1. And remember, this is important, a is just a positive number. This is to make the basic formulas a little bit more user-friendly. I think a lot of times when we look at formulas like this, they look a little bit ominous, but again, these user-friendly additions that we have here make the integral form useful in many ways, not only in mathematics, but in your physics and your engineering classes. Now, the second integral that we have here is the integral of du divided by a squared plus u squared, which is equal to 1 over a inverse tangent of u over a plus a constant. And again, just remember, for the inverse sine form, we don't have the 1 over a. That's sometimes a blessing, especially if you just forget about it. And then, of course, the very last one, which was maybe the most lengthy to derive, we have the integral du over u times the square root of u squared minus a squared, which equals 1 over a times the inverse secant of the absolute value of u divided by a plus a constant. Here we would need the absolute value of u divided by a greater than 1 for this integrand to be defined. So again, what we want to do is look for patterns that would suggest one of these. And in some cases, we actually have problems where we have to do a lot more algebra and break up the integral into two pieces. And I want to show you how to do that. Now, for the first integral, I pulled these from your book and from WebAssign homework problems. And the first one looks like this. So here's our example. And we have the integral of 5 dx divided by 36 plus 9 minus x quantity squared. So it's good to start out with one that's relatively straightforward. We don't really have to do much work here, but this is kind of a warm-up. So what we can see is this most likely imitates the inverse tangent form. So let's just remind ourselves, once we think of it, let's just write it down. Then we have basically a little roadmap that tells us what we need to do. So we have the integral of du divided by a squared plus u squared will be 1 over a inverse tangent of u over a plus c. So it's kind of good to start this way until you get into a groove, and then you're probably going to be fine with what you need to do. So now we see that we're pretty much ready to go. We can rewrite this to match this. We've got definitely an A, and we have also a U. So what we can do is just write in the next step, and we'll identify these. The 5 we can extract, and we have a dx, and then we have a 6 squared, which is the 36, plus 9 minus x quantity squared. And so just to give a little bit more room here, let me move this equals sign over some. Now we can identify A is equal to 6 and U is equal to 9 minus x. Now what we want to do is take the differential. So du is equal to negative dx. Now everything looks good, but in our problem, we have a dx and not a negative dx. So what we can do in this particular case is insert the negative and then pay for it, just like we always do when we're doing integrals. So for instance, we'll have a negative 5 that will counter the negative that we put in here with the dx. Now again, remember, we can move constants in and out, and using the linearity properties of the integral are very useful here. And then we have 6 squared plus 9 minus x quantity squared. So when we look at this and we compare this in this particular problem, here's the a squared, here's the u squared, and here's the du. So again, this is table ready. The idea here is we think of what we've written over here in red as an integral table. And the integral table basically tells us what we need to be able to do. That is, when we think about this, let me just align this a little bit better. There we go. Let's see, oh, there we go. That's that. All these adjustments here, you touch things and you make adjustments you don't always want. Now, so we see this is table ready. So now we can just fill everything in. So using our formula, we have negative 5. And then of course we have the 1 over a, so that's 1 over 6. And then we have inverse tangent of u, and our u is 9 minus x. Of course, our a is 6 plus an arbitrary constant. And now what we can do is just clean this up. Let's just go ahead and move the negative 5 over. It's nice to keep everything nice and separated so that you make sure you don't forget any factors. So we have negative 5, 6 times the inverse tangent of 9 minus x divided by 6 plus an arbitrary constant. So again, when we look at problems of this nature, we see this is a very straightforward problem, but it's straightforward because we know the form for the inverse tangent integral. So again, we identify the form as inverse tangent because that's what's involved in the antiderivative. So these Pythagorean integrals are ubiquitous in mathematics and science. The only problem is when you start changing powers up, you get elliptic integrals, and those are much more challenging. And as you continue your work in science and engineering, you will see those. Now let's look at another example. Now here, what we want to do is look at the following example. That is, we have the integral of 1 divided by x times the square root of x to the 4th minus 4. And this is similar to one that we did at our last lecture. But again, what I'm trying to do is get you back into the routine so that the more challenging ones will go a little bit more easily. Now, we look at this and we think the inverse secant problem or the inverse secant form. So it looks like we can go ahead and write that down just to remind ourselves. So the integral of du, u square root u squared minus a squared equals 1 over a inverse secant absolute value of u divided by a plus a constant. So that's, I'll put a box around this. That's our integral table right there. And this is usually considered a basic form since it occurs so often. Now, so what we want to go ahead and do is dress this up so that we have the u and the a identified. So that'll be fairly easy to do. So we have x, and I'll go ahead and use brackets for now. We have x squared, quantity squared, minus 2 squared, raised to the 1/2 power. Now, when we look at this, we see we have u is x squared, taking the differential, du is 2x dx. And then, if you will, what is a? A equals 2. Now, when we think about this and we see what we have, we know this is pretty much rigged. If u is x squared that we see we need here, we need an additional factor of x here. But that additional factor of x will be balanced by the x that we need here. So what we can do is the following. I'll go ahead and use a different color. We're going to multiply by x. So here we have x. We already have the dx, just to kind of give you an idea of what's going on. And then we need the 2 in the differential. So we'll put a 2 here, and then we can balance the 2 right there. So what we're doing here is just dressing up this integrand algebraically so that it fits our integral table, so to speak. So now we can actually write it correctly. Notice here, we have the du. And notice here, we have u. Here, of course, we have u squared. And then here is the a squared, right there. So this 2 needs to come out. So we have 1/2 2x dx. We have x squared. I'll go ahead and write the square root symbol. X to the 4th. Now we'll just go back to the original symbols. X to the 4th minus 4. So now that we see we have the table ready, this is almost table ready. Well, actually it is table ready. We just factored the 2. So I'll re-emphasize that, table ready. So formally, what we have here within the integral sign is mimicking what we have here. So that means we can move forward. So now we have the 1/2, which just comes along for the ride in the algebraic process. And then we do 1 over a. So that's 1 over 2. We have inverse secant of u. Of course, now we have the absolute value of x squared, which is u. So we can eventually remove the absolute value. That won't be needed. And then, of course, we have 2 plus a constant. So let's go ahead and clean this up. This will give us 1/4 inverse secant of x squared over 2 plus a constant. Now, again, and what's important here is we just need to make sure that as we're working through these problems, that we keep in the integrand exactly what we need, and then remove anything that's not necessary. That way we keep the arithmetic correct. It's really easy to forget a 1/2 or to leave out a negative sign, anything like that. Anytime you're doing calculus, you always have to be careful, double check, triple check what you do. Now, Let's look at some examples that require us to maybe make some more modifications. So as you do your WebAssign homework, I want you to be familiar with the fact that as we work through these will be examples that we'll see again and again in our additional work with integrating techniques. So I want you to really develop some comfort with this so you build your confidence. Now let's look at this example. So we have a definite integral. The lower limit is the natural log of 2. The upper limit is the natural log of 4. And we have e to the negative x divided by the square root of 1 minus e to the negative 2x dx. So when we look at this, we automatically think inverse sine. We know that formula. It's easier than the others. And so we're thinking we don't even have to do much work here. So let's go ahead and dress this up. So we have natural log of 2 as the lower limit, natural log of 4, and then we have e to the negative x. I'll go ahead and write the dx right beside the e to the negative x. And then we have, and I'll overkill this a little bit. I wrote the radical sign that time. So we have 1 squared minus e to the negative x quantity squared, just using laws of exponents. Now we see that we do have a inverse sine form. So let's write everything down. A is 1, u is e to the negative x, and then of course du is the negative of e to the negative x dx, using the derivative of the natural exponential. So what we can see is that all we need is the negative sign here, which we can easily place here and then compensate for. So let's go ahead and do that. We can do it in the same process here, but let's move one step forward just to make it a little bit easier to follow. So we have the negative of the integral, negative e to the negative x dx. And then, of course, we have 1 minus e to the negative 2x. Lots of times we can just relax our notation. Once we've identified the a and the u, we can go back to the original symbols and not have lost anything. So this is table ready. And of course, I need my limits of integration. How convenient to leave those out, right? So table ready. Now, one thing you will notice here is that we can often change the limits, and that is often up to you. There are cases where it makes sense to change the limits and cases where it may be more advantageous not to. So what I'm going to do here is just go ahead and work it through and not change the limits, just to remind us how we do that. So now remember, we don't have the 1 over a, but that wouldn't matter if we forgot it anyway, since a is 1. So we have the negative here, which comes along in the algebraic process, inverse sine of e to the negative x, evaluated from ln of 2 to ln of 4. So remember this negative sign here came into being when we had to manipulate the integrand to get the proper du. So don't forget about it. So now we can factor the negative, so to speak. So we have inverse sine of e to the negative ln of 4 minus inverse sine e to the negative ln of 2. So now we can use our properties of logarithms, namely the power rule. So we have the negative. I'll just leave the negative out for now, then I'll run it through when it's convenient. So we have e Now, of course, when we move the negative upstairs to the 4, we get 4 to the negative 1, or just 1/4. And then the same with the negative ln of 2, we get inverse sine e ln of 1/2. Now we can apply the fact that the natural log and the natural exponential are inverses. So we have the negative. So this will just leave us with 1/4. So inverse sine of 1/4. Now we don't have a nice value for that, so we'll leave that alone. But now here, inverse sine of 1/2. And we know that from the unit circle. That's just pi over 6. So now if you want, you can just go ahead and run the negative through, negative, negative, and then we'll translate. So like I said before, here, we'll leave this as it is, but we'll just write this as pi over 6. That's the equivalent value, minus the inverse sine of 1/4. Now, here's an important point, and this is very important. If we were doing this problem in WebAssign, this would be exactly what you would type. You could use arcsine instead of sine superscript -1. WebAssign will take either. Both of the notations are legitimate. But the main thing here is that we can do the interpretation of the inverse sine of 1/2 because we know it. We know that from the unit circle. So that's fine. But the main thing is that we don't have a simple value for this. So we don't approximate it. For instance, if the problem requests a 3 decimal approximation, then you can do that. Okay. But otherwise, without that request, this is the response that must be typed. This is exact. And so when we do math problems, the assumption is that the answers we provide are exact. And so we need to be careful that we do exact mathematics. And then if we get to the end of the problem and an approximation is requested, then we can give a good approximation because we haven't introduced round off error. Okay, so good example. Now let's look at a problem that provides, and when I say provides, more algebra. For the problems we've just done, the actual form was very apparent to us. And of course, the form will be somewhat apparent for any of the problems, but you may start out on one track and then end up changing it because things don't work out like you had anticipated. So let's look at this example. Here's a good example of what I was just talking about with algebra. So we have x minus 4 divided by x plus 2 quantity squared plus 16 dx. Now, how you adjust integrands is usually a very personal thing. It's like doing transformations in college algebra and pre-cal. As long as the result is correct, the order of your transformations is immaterial. That is, if you do the transformations correctly and the result is what is requested, then you're fine. So there's not always a unique path to developing a particular function. And the same is true here. So what we can see is this kind of looks like the inverse tangent form if we just got rid of that. We'd say, oh, that's an inverse tangent form. But what we have is what appears to be two integrals combined. That is, we have a calculus 1 integral combined with our new inverse tangent integral. So what we want to do is first think Cal 1. So we'll use a u and then maybe a w, so not to reuse the same variable. So we'll say u equals, well, let me just go ahead and write the whole thing. We have x plus 2 quantity squared plus a 16. So we're thinking of this like a du over u in calculus 1. Okay, and so we're thinking we can make some adjustments. So du will just be 2 times x plus 2 dx. Of course, the 16 going to 0. Now, at this point, we have two possibilities. If you look here, we need a 2x. We have an x. So we can introduce a 2, pay for it, and then introduce the factor of 2, and then pay for that, and then break up the interval. So here's what we'll do. So this kind of gives us a roadmap. So first, we need an x plus 2 in our differential. So we'll say x plus 2 minus 2. And of course, we have a minus 4 right here anyway, so we'll just leave that right there. And downstairs, we'll go ahead and write it. We won't expand this. You don't have to expand it, but I guess eventually we will. So if we look here, we've got the x plus 2 that we're going to need if we break up this integral algebraically, but we need the factor of 2. So now I'll go ahead and use red. We'll get the 2 times the x plus 2 with that 2, and then of course pay for it. Now what I'm doing is not unique. It just really depends on what the problem gives us. And so how you do this is not unique. So don't worry that your procedure has to mimic mine. This is just a way of looking at it that seems to be fairly straightforward. Now just remember, we want to get this du in our problem, and we do have it. And so however you do that, you just have to do it legally so that this actually equals this. And if that's the case, which it is, then we're in good shape. So now let's go ahead and reduce this a little bit, and then we'll break it up. So we have 1/2, and we have 2 times x plus 2 right there. And now notice here, we've got a 2 and we've got a -6 here. So we're going to say minus 12, just to reduce that, divided by x plus 2 quantity squared plus the 16 dx. Now you can see why we did this, because if we break this integrand into 2 pieces, we have our du over u, which we've constructed from here. And then what remains is an inverse tangent form. So now let's break it up. That is, don't forget our friend, the 1/2. So we have 2x plus 2. I'll go ahead and put the dx right there. And then downstairs, we have x plus 2 quantity squared plus 16. That's our first integral. And then the next one, we can go ahead and write down. So we have plus 1/2. And if you like, you can go ahead and factor, as I've written it here, you can go ahead and factor the -12. No problem with that. It's just using linearity. And we have dx. I'll write the 16 first because we usually like to do that when we do the inverse tangent form. Not that it matters. Now, when we look, we're pretty much ready to go. Note that we can think of this as a w substitution since we've used the u here. So you can think, okay, well, we have a equal to 4 because 16 is 4 squared, and w is x plus 2. So dw is just dx. Well, they don't come any simpler than that. This is ready to go. That's table ready. And we've already worked on this. This is ready to go. Notice we have u here and du here. Both of these are table ready. And I'll write that in blue. Table ready. That's a good phrase to get used to if you're tutoring someone. It's almost like a signal that says, okay, you've done everything you need to do, so now we can move forward. Now, of course, just remember that the du over u is our natural log of the absolute value of u. So the 1/2, it just comes along for the ride. We have natural log of u, and that'll just be, if you want to expand it, we can. Let's go ahead and do that. That's x squared plus 4x plus a 4 plus a 16 will give us a 20. You don't have to do this, but that might have been bothering you a little bit, but it doesn't matter if you do it or not. And then over here, we have the -6, so we have -6. And then with the inverse tangent form, we need 1 over a inverse tangent of u, which is x plus 2, divided by a plus an arbitrary constant. Now, if we look at this, we're good to go. Now, I will say this. You don't have to expand this if you don't want, but it's sometimes customary. In a Cal 1 class, we would do this. In a Cal 2 class, we do it this way because that's the forms that we have by convention. So now when we complete this, we just have 1/2. Now, of course, remember, this is absolute value argument here, but this is always positive, so that's why I've left that out. But just to be completely correct, put the absolute value in so that in the future you don't forget it, because this could change sign and you don't want that. So we have natural log now of x squared plus 4x plus 20. And if you will, go ahead and just write the du over u integral from Cal 1, natural log of the absolute value of u plus a c. That's what I used, and we know that very well. And then, of course, we have a -6 over 4, which is just a -3/2 if we divide by 2. Inverse tangent, x plus 2 divided by 4 plus a constant. Now, when you look at problems like this, you can see how we combine our knowledge of different integral forms to do a more challenging problem. And I will say this, when you see problems like this, as you learn more integration techniques, you'll look at this and say, what am I doing? You'll think like, well, you've got to apply some fancy technique that you learned in a later chapter in this course. And you don't, you will have just forgotten this. And so many times I'll have students come by the office, that is when we were on campus, and they say, I can't do this integral. I don't know, I'm so good at integrating. And I said, it's too simple. It's something you learned at the early part of the class. So just remember that sometimes integrals are quick to do and others actually require a little bit of preparation to move forward. And this is one of those examples, but a good example. So one type of problem that's always popular in WebAssign and also popular in this type of work, because what ensues is one of our new forms. It's called the miscellaneous substitution. And you know, the miscellaneous is just the algebraic manipulations that we do to convert an integrand into something that we understand. So let's do what we call a miscellaneous substitution. Miscellaneous substitution is a useful technique that really hits the integrand with lots of algebra and completely transforms it. So it's not the standard substitution that we learn first based on the chain rule. So here's the problem that we have. And the natural exponential lends itself to some really interesting little problems like this. Again, a lot of times when you see certain integrands, if it's something that doesn't fit anything that you've done or it doesn't appear to fit, try the miscellaneous. I mean, it's certainly not a waste of time. So when we do this, the only thing that we can do is let the radical be our substitution. So again, miscellaneous. So let, I don't usually say let, but since this is miscellaneous, I'll do this. Let u be the square root of e to the t minus 3. So now we can square, just for ease, u squared equals e to the t minus 3. Always techniques vary, and so nothing is set in stone, so you can always vary from what I do. So now taking the differential, 2u du, and then of course the differential of e to the t minus 3 is just e to the t dt. We enjoy the natural exponential. Now what we can see is that we have a substitution for the radical. We just need a substitution for the differential dt. So let's solve for it. That's the beauty of this. So we get 2u du. I've got t's and u's running around, mix and matching, right? And so now divide by e to the t. But when we look at this equation here, e to the t is just u squared plus 3. So we have 2u du, and then using the previous equation, we simply get u squared plus 3. So here we just solve for e to the t, and we substitute it here. Now, of course, this makes much more sense. We can write dt in terms of u, and of course, the radical was the substitution for u. So that puts us in a good situation. So let's go ahead and do the miscellaneous substitution. So we have u times 2u du. So we're just going to do some division, but it's not difficult division. So this gives us 2u squared divided by u squared plus 3 du. Now, of course, we just divide by u squared plus 3, but that's easy since we only have one term up here. So the u squared into the 2u squared will just give us a 2. And then we're going to have a 2 times a 3 and subtract. So that's going to give us a negative 6 divided by u squared plus 3. So that's not hard to do. So that's our new integrand, which we understand completely. Now, when we look at this, so just your basic polynomial long division, now you can see this is easy, but this has the inverse tangent form. So I think what's important here, and let me just adjust the light here, so everything looks a little bit less flushed out. So now what we can see is what we thought, or at least initially, we said, okay, let's do miscellaneous, see what we get. And so now we're pleased that we actually have a form that mimics the inverse tangent. That is, we have a form that we know how to work with. So let's go ahead and move forward. So now we'll break this up. So we have 2 times the integral du. Well, we wish all integrals were that easy. And then now, if you will, we have a minus 6, the integral of du, and we'll write it like the form we are used to. This is real simple now. So 3 we'll write as the square of the square root of 3. And then, of course, u is just u. So that couldn't be simpler, u squared. So again, we wish all of our integrals were this easy. Now, if we had started with this, that would have been simple, but we had to work with a different integrand. And we see how the technique of miscellaneous substitution actually makes this very doable. So now we just get what? 2u. And if you will here, u is u. Well, we just have u equals u. And a, obviously, is the square root of 3. So now we can write that in. So we have minus 6 divided by the square root of 3. Usually I'll just do 1 over root 3, but this one's pretty straightforward. And we have inverse tangent of u divided by a, which is root 3, plus a c. So now the only thing we have left to do is just replace u with this definition here. So this gives us 2 times the radical e to the t minus 3. And then WebAssign doesn't care if you have radicals in the denominator, and I certainly don't. So we have 6 over root 3. And then with the inverse tangent, we know that u is square root of e to the t minus 3, so we can write that under 1 big square root, include the 3. So we have the 3 upstairs and the 3 downstairs, just like that, plus a c. So now what we're seeing is that we would never expect this integrand from that integral. That's why we remind ourselves that the process of anti-differentiation is just more difficult than differentiation, because the process requires recognizing a pattern. When we differentiate, we move forward because we recommend, for instance, we recognize patterns. And so we do that and move forward. Like we say, okay, we use the chain rule. And most functions that we deal with in calculus, we know how to differentiate, or we learn how to do it, and it's not as difficult. Or we use the product rule with the chain rule, or the quotient rule with the chain rule. So the setup may require a lot of algebra, but it doesn't require the amounts of intuition that the integration does. So we need to keep that in mind as we work through these. So let's try another one. Now, the next one is a standard problem from your WebAssign, and it utilizes the same technique that we used in the problem where we had the U and the W substitution. So let's go ahead and look at this. So in this particular case, this is a definite integral, so it gives us a chance to do a little bit of everything. So we have the integral of 2 to 3. This is a popular example, or a popular type example. So we have an integrand in the numerator of 2x minus 3. And downstairs, so we get to use a lot of algebra, we have 4x minus x squared dx. Now, when you look at problems like this, you're thinking, well, this looks like the inverse sine form, but we have stuff. I mean, if we get rid of the 2x, then that would be completing the square, and we'd have an inverse sine form. Hopefully that we would retain the negative where it needed to be in the square of a in the front, so to speak. So that's what we would think would be an easier problem. So we're going to have to do this just like we did in the previous example with the inverse tangent. So first, what we want to do is say, okay, we're going to have to break this up, but let's figure out the algebra that we're going to need to do to get to that point. So we're going to let u be, I'll just go ahead and write this as negative x squared plus 4x. Go ahead and write that first and see what we get. So du will be a negative 2x plus a 4 dx. Now we can say, all right, well, we need a 2x in our example. So we'll say du, in this particular case, let's factor the negative 2. We get negative, or excuse me, let's just factor the negative. We want to keep the 2. 2x minus 4. So that would be a twofer, just like the last one. So now let's kind of look at this and say, this is not so bad because we need a 2x. We have. we need a -4. So what we can do is we can place the -4 in algebraically, pay for it, and then once we've done that, compensate for the fact that we need the negative here. So then we can dress up our calculus 1 integral. And then, of course, what would remain would be the inverse sine form. Now, we know we're going to have to complete the square here. So let's go ahead and do it. Negative x squared plus 4x. So we're going to factor the negative to make it monic. All this college algebra. It's amazing. So now we have the -4. So half of that is -2. So +4 minus 4. So now, of course, we have a perfect square here. This is just, well, I'll go ahead and use the brackets. This is just x minus 2 quantity squared. And now notice, so that part right here becomes that. And then we have the -4. And now as we complete the problem, we run the negative back through. So that gives us the 4 minus x minus 2 quantity squared. Now this is not hard to do, but it is very essential because now this fits the form of the inverse sine radicand. So that's extremely important. So often when we have the inverse sine form, we look at that and say, well, that's going to require a little bit more work, but we can do it. So now let's go ahead and dress this up so we can actually use this. So what I said before, we're going to go ahead and add the -4 and then pay for it. So we have 2 as a lower limit, 3 as an upper limit, and we have 2x minus 4 plus 4 minus 3. Again, you can leave out steps, but put in enough algebra so that you can track what you're doing. Otherwise, you may come to grief. And now this is dressed up. We have the -4. That is, when we look at this, we have the 2x minus 4, which we need in the differential. But now we need the negative. So we'll do what we did before with the 2. Now we'll do the negative and then pay for it. So when you look at this integrand, it's equivalent, or this integral, it's equivalent to this, but now it sets us up for these substitutions. So now let's go ahead and write this out. So this gives us the negative 2 to 3 of, we have the negative 2x minus 4. Now notice here we have a 4 minus a 3, so that's just a 1. So we have plus 1 divided by the square root of 4x minus x squared. Now notice here, and this is something I just noticed, we have the 1 here, but we have the negative here. So that'll be a negative. I was going 2 steps ahead and I don't need to skip steps. So that's still a negative. Okay? So now, again, just remember this negative is applied to all of this. So we need that negative there. Now we can break this up. So we have the negative of negative 2x minus 4. And of course, Professor Ron likes to leave out his dx, so we need the dx. We're lost without the differential. And then we have the square root of 4x minus x squared. That's good to go. And now, of course, we have the -1 here, which we corrected, made negative, gives us a plus. And then, of course, we have the limits 3 to 2. Always something to remember. Now, one thing you might notice here, and this is important, we can go ahead and fill in this with this. since we know we need this form for the inverse sine. So we replace the 4x minus x squared radicand with 4 minus the quantity x minus 2 quantity squared, and of course the dx. So now, wow. So let's do one more step here to make it a little bit easier. I could have done it there, but I didn't want to. So we have the negative. We have 2 to 3. And I'm going to bring this radical upstairs because we've got the u and then the du, so to speak. So we'll have the 4x minus x squared to the negative 1/2 times the differential. So we have negative 2x minus 4 dx. And now, if you will, this is really easy. This turned out to be the hard part. We have a equals 2, and we have, well, I guess I'll have to use a w since I've used u over here. And I may have reused u before. If I did, forgive me. This will just be what, x minus 2. So dw equals dx. So this is table ready. Now this is table ready too. So we can go ahead and write this out. This will be inverse sine of x minus 2 divided by 2, evaluated from 2 to 3. So that part ended up being very simple. I mean, wow, that was easy. Now, this is just add 1 divided by the new power. We have the power rule. We have u to a power, and we have du right there. So that's table ready also. So again, we have the negative that's already out there. So when we add 1 to negative 1/2, we get what, a positive 1/2. So we reciprocate that and get a 2. So again, add 1 divided by the new power. Add 1 to negative 1/2, get a positive 1/2. Division by 1/2 is multiplication by 2. But the negative was already there, so don't forget that. So this gives us 4x minus x squared, excuse me, to the positive 1/2, 2 to 3. Wow, lots of little bits in these problems. And now we can go ahead and start working on this. This will be plus inverse sine. Go ahead and substitute the 3. That'll give us a 1 over 2. At least that's simple. And then if we substitute the 2, we just get a 0. Now let me get rid of all the extra stuff on the screen. There we go. The technology is nice, but it does what you tell it to do, and sometimes you're not sure you're telling it to do anything, but it happens. Okay, so now let's go ahead and substitute. We have negative 2. So substitute the 3. This will give us a 12 minus a 9. So we have 12 minus 9 to the 1/2 power minus, and then we substitute the 2. This will be 8 minus a 4, which is 4. And that's a perfect square. Now, of course, the inverse sine, we've done this before. 1/2 is just pi over 6, and the inverse sine of 0 is 0. That's our friend. So now we have negative 2, and we've got what, the square root of 3. And then, of course, here, the square root of 4 is 2, so we have minus 2 plus pi over 6. Now, again, when you put in all the steps and you discuss everything in detail, it's a long problem, but it's a very doable problem. And now when we run the negative 2 through, what do we get? Negative times the negative, that'll be a positive 4, minus 2 times the square root of 3, plus pi over 6. Now, I want to say this again, this is important. if this is a WebAssign problem, and usually I like to assign problems like this would be the answer that you would type. That is, unless an approximation is requested. If an approximation is requested, they will give you the number of decimals. So you work the problem exactly, and then if they ask for an approximation, then you provide it. But you have an exact answer with which to work. So again, if there is no direction about approximation with integrals, with anything, and those of you that have used WebAssign, you know what I'm talking about. But those of you that are new to WebAssign, be aware, an exact answer is always expected. Just assume that it's expected. Now, we have just one more example. So like I say, the idea here is that I want you to be able to do your homework and your quiz. Again, the homework will be due Monday by 11 p.m. and then the quiz will be due Tuesday by 11 p.m. So this is my way of keeping you current with your work. I think it's important that each week you have some homework that you have to complete, and this keeps you on a schedule. Unfortunately, getting behind in math is really not an option. We always want to stay current in our mathematics so that we always work into new sections in the know. So now here's an example. So again, like I said before, when it comes to doing these types of problems, it's important to realize that not only are we using what we already know, but we're combining what we know with some new techniques. So let's look at this one. We have the square root, the integral of the square root of 3 to 3. And then we have 1, we have x, and we have the square root of 4x squared minus 9 dx. Now, after doing the last problem, you're thinking, well, you can't find another problem in this section that's going to be more challenging than that. The problem wasn't overly challenging so much as it just had lots of steps. And that, of course, does make a problem harder. But the idea is when you're doing integration problems, you simply have to utilize the limited knowledge that you have. We don't have as much knowledge about antiderivatives. So as you work with them, you have to be careful that you're applying techniques that you know are indeed valid. Now, here you're thinking, we're not going to have to do any grand algebraic gesture because this looks like the inverse secant form. So we can go ahead and move this forward and use our fundamental theorem in that way. So first, let's go ahead. Now you're going to see that after the more challenging problems, we can move this forward very nicely with much more confidence. Again, double, triple check your work. You see, as I work through examples, it's easy to leave off limits. It's easy to drop a sign or drop the dx. Always check your work to make sure that you can move forward with confidence. So we have 1, and we have an x, and I'll go ahead and just use a bracket here. So the 4x squared is just 2x quantity squared minus 3 squared. Always give yourself plenty of room to write the radicals. And if you don't want to write the radical, go ahead and just use the 1/2 power. Now, when we look at this, we see we're set up for the inverse secant. That is u equals 2x, du equals 2 dx, that's easy enough, and a equals 3. Sometimes the most simple algebra can confound you. We will make careless mistakes when we don't even intend. So again, double, triple check. Now, when we look at this, we see that we have the dx, but we need the 2, so we can put in the 2 here, and then of course balance the 2 here which will give us the U that we need. So that was just too easy. So let's go ahead and write that. When they work out nicely, we're excited. So again, we'll have the 2 dx. I'll go ahead and move that into the numerator and balance that 2 here. That gives us the 2x. And now, of course, we can go ahead and write the radical again, 4x squared minus 9. And this is clearly table ready. So again, when we work with these types of examples, we just dress it up algebraically and we're good to go. So now we'll fill everything in. And I will say this, when we have the inverse tangent and the inverse secant forms, we always have the 1 over a, but we don't have anything out here, so we don't have to worry about that. So we get 1 over 3 inverse secant of the absolute value of 2x divided by 3, evaluated from the square root of 3 to 3. Now, again, at this point, we're simply going to use the fundamental theorem, and then, of course, keep thinking exact answer. So we have 1/3. We have inverse secant. So we replace the x with 3. That'll give us a 6 over 3. The 3's absorb, and that just gives us a 2. We can do that. That's not difficult. And then now minus inverse secant and replace with the square root of 3. I'll write that out and then we'll reduce that. So we have 1/3, we have inverse secant of 2. And now, of course, the square root of 3 will absorb into the 3 to give us inverse secant of 2 divided by square root 3. But now, this is what I was saying before. With our choice of the inverse secant, we can use the reciprocal law. I mean, you can go ahead and say, well, we know what these are, but you can think of this in terms of the inverse cosine, which we can actually use because of the reciprocal law. So you can do that and say, I know what these are, or you can use the reciprocal law, and this will be inverse cosine of 1/2 minus inverse cosine of root 3 over 2. Most students just say, oh, I know inverse cosine, so the secant is just the reciprocal of that. But this is now something that should make you feel good about how we actually define the inverse secant function. So we get 1/3. So inverse cosine of 1/2 is pi over 3. And then, of course, the inverse cosine of root 3 over 2 is pi over 6. So we can factor the pi. So this is pi over 3. And get a common denominator of 6. So 3 into 6 is 2. So we have 2 minus 1. So of course, that'll just be a 1 times pi. And then a 3 times a 6, which is an 18. Again, an exact answer. So in many instances, the problems will request exact. There are times, however, when an approximation will be requested, but you determine an exact response. I tell my students, I'm always more interested in your being able to determine the exact response. If an approximation is needed, then fine, you don't have anything to worry about. But there are times when I'm very happy that the problems I select will require you to give an exact response. But there are occasions when an approximation is needed, or an approximation is useful in thinking of things in a magnitude perspective. So it's all good. Now, Again, as a moment of summary, after we have completed this, which we have, we're going to move into some concepts dealing with applications of the definite integral. And so we're going to be talking about areas. We're going to be talking about volumes of solids of revolution, techniques for that, some arc length, surface area, work-related integrals, and center of mass. Now, for you physics people and engineering people, this will be very interesting and certainly will be a prelude to some of the curve theory that you do in Calculus 3. So what I wanted to do today, since we did not have a formal lecture, is to go ahead and record this information so you can go ahead and finish working on your integrals in section 8. So again, remember, Monday by 11 p.m., homework is due. So this will be 5.7, 5.8. And I've talked with a lot of you. Remember, you do your homework on WebAssign. And that's how I know that you completed it. There are additional problems on the daily schedule, which are optional. That's what we used to use, or I used to use, when students would say, are there additional problems that I can work? And you're always welcome to work those, but I'm grading you on the WebAssign. So work as many as you like, but know that you're graded on the WebAssign problems. And your quiz is also on WebAssign. So you do your work and then you fill in your responses. And by Tuesday, by 11 p.m., we have quiz number 1. Now remember, the quizzes are timed assessments. So do not attempt the quiz until you're ready to take it. Once you start the quiz, then the clock starts ticking, so to speak. And so you have the time that's given to you to actually execute the quiz. So do not access the quiz until you are ready to take it. That again is a timed assessment. Remember, the totality of the homework is 10% of your grade, and the totality of the quizzes is 10% of your grade. So that's 20%. That accounts for 2 letter grades. So that's a significant portion of your work in this class. Just like the final exam is 30%, and the 4 semester tests that you take will count 50%. So there's plenty of room to work hard, to make good grades, but it's important to stay current. So again, go ahead and complete this work so you'll be current. Again, I wanted to go ahead and finish up the material on the integrals. Practice these integrals. Make up your own integrals if you want. Lots of students will try to come up with their own integrals and see if they can solve them, okay? So I hope that everybody's doing well, and I hope that you stay safe, and let's hope and pray that the worst of the storm will stay away from us. At least I know that we are to the west of the storm, and so as it moves, it's going to throw more rain to the east. So unlike Hurricane Harvey, we're actually in a better geographic position. So let's hope everything stays just that way. Okay, you all have a great day. And I'll go ahead and stop the share and sign out. So everybody have a nice evening, and I will download this from the cloud and put a link to this on Blackboard so you can view it. Thanks, everyone.